So let me present my screen. So I hope everyone can see my screen.
Yes.
Okay, great. So thanks a lot for joining this session. It's just a brief introduction. Um, I'm the founder of VerticalServe. This company was founded in 2013, and we are a partner. We are partners of Amazon, Azure, Google Cloud, Confluent, Cloudera, Databricks, and all those companies. And we are a niche product and consulting firm. So we started in 2013 as a product company. We built Insight Lake data platform, data management, data science products. And lately, we have been building some Gen AI products and accelerators and contributing in wider open source society. We are heavy, deep into technology. We have last 11 years, we have worked with 60 plus customers across all industries. And just a timeline, founded in 2013. We are a New York, New Jersey-based company, a small company, like 50, 60 people spread across USA, Canada, and India, in India and in Pune. So if you see the journey, we started our AI and ML practice in 2016, worked with very large financial firms like Barclays, JP Morgan, Southern California Energy, and all these companies. We started leveraging a lot more deep learning. Even before that, we used to use like machine learning in many different use cases. We dig deeper into many implementation in deep learning around 2016. And you will see the correlation when some of these large language models or language models started around that time frame as well. So we will connect the dots from there to the transformer-based architecture in the latest large language models. We created a Gen AI practice within VerticalServe in 2023, and we have been guiding a lot of customers doing architecture sessions with them with their use cases, whether it's a churn prediction, new campaigns, building contact center, and all those things using Gen AI. So that's our primary motivation. And because we are a startup at our heart, we always believe in contributing back to the wider ecosystem. And that's why some of these sessions are also important. So we are doing some of these fundamental sessions with companies, as well as we are doing these webinars so that these can get recorded, and then we publish them out on the websites so that people can look into these things. Starting on the language processing side, I'm assuming like some of you might have built models. Some of you are core data scientists tinkering with deep neural nets. Um, some are just looking at purely as a use cases perspective, that you are building use cases, you are utilizing these components. So whenever I do these sessions, I always look at the problem first at a very, very high level and see and connect the dots from very high level blocks to the lower level implementation. I work as an enterprise architect at various firms also. So whenever I work with CTOs and CIOs, I try to lay out a high building blocks and then double click on these blocks to keep opening the layers and explain them the inner workings of those layers. So we'll do the same thing in today's session. So this slide, it talks about like a 2024 US election between Joe Biden and Donald Trump, right? And it's a simple paragraph. As a human user, you will see the paragraph, you will go through that, you will attend to some key salient features of this text, like 2024, Joe Biden, Donald Trump, what are the key issues, abortion, immigration, healthcare, and all those things. And this is how our mind works. And with this text, once we read this, we can, if we know from English to, let's say, French also. We can translate that. We can summarize this text, that what it is about as a human. We can classify that whether it's a positive, negative, or what type of text it is, whether it's related to election, politics. So we can categorize those things. There is a named entity recognition, NER, which is like entity extraction. So NER, basically we can extract out, let's say, date time 2024. We can extract persons, Joe Biden and Donald Trump. So we can do those entity extraction. We can also build a chatbot where, using the chatbot, just like Chat GPT, we can ask questions that when is the election, it can respond back that, okay, that's 2024. So this is a language block, and again, as a human, our mind, our brains are trained, our neurons are there, which are uh, getting some information, storing some information, and then we are able to perform actions on top of that, right? So same thing, like if we need to jump into a little bit of the language structure, and we'll see how we can model all of these things as a model, and uh, build some of these use cases which we just looked at it, like translation, summarization, classification, entity recognition, chatbots, etc. So again, before digging deeper into modeling this, we need to understand what language is. So language is a very complex structure, right? As humans, we have developed these languages over a very long period, and the language have structures, meaning, grammatical, syntactical aspects. So if you see a language is, when we speak, the sound has different components, like phonemes are there, and it's a category of a phonology. How we speak it, the tone difference can make a word totally different. So phonology and all we will not cover in today's session. We will have a set of extra sessions on transformers, covering audios, videos, and multimodal aspects. But today's session, to keep it very, very simple and high level, we will focus more on the language side, which is the textual language side. So when you talk about the language has two parts, structure and meaning, right? So structure means the morphology, how a word is built using characters. Syntax, what is the syntax of that word? And when it comes to the meaning of the word, like, so when I say bank, bank can be a financial institution, but bank can be also a river bank. A meaning of the word depends in which context it is used. So it is the semantics of that word, how it is correlated to different other words, where exactly it lies in the language spectrum. So, for example, he was at the bank of a river. If we have a sentence, right? So, definitely we know the bank. We are talking about the edge and that area where he is probably relaxing, sitting there. It's not a financial institution and all. So, knowing the language is very, very important. And when you look at the language, when you break it down, a language you can easily put some sort of a rule or a structure around it. So there are, let's say, if I have a sentence called like, I drive a car to my college. So in this, like, we have a particular structure, which is like a noun phrase, verbs are there, we have a positions, we can have adjectives and all. So when we do the language modeling, there are multiple aspects, which is, we talked about the syntax, morphology, meaning, semantic meaning of the word, structure of the language, grammatical structure, relationships. So there are many complex nuances when we do the language modeling. And uh, again, in the early days, 2014, 15, and early days when Stanford released like some of the NLP libraries, and I'm pretty sure like some of you might have used NLTK, Spacey to do natural language processing and all. And you must have used some of those library functions, like to do the stemming of the word, to do the lamentation and all. So some of these things are very important. Like when we were building some of these rules around understanding the language or modeling the language, we used to take the word, stem it, which stem it is determined from by removing the suffixes and then getting the laments out, and do the tokenization, and then finally build basically those kind of models. So now let's talk about like what changed actually from those early days to the current models. Chat GPT is a great example which changed everything. Everybody is talking about generative AI. So before jumping into these generative AI and the models, right, and their history, how they evolved, here is the simple snippet of a chat GPT where you ask a prompt that write 50 words on USA election, and chat GPT will basically respond with a very brief summary. It's a great summary actually, and it understands the language really well. It can generate the languages. It can generate the content related to whatever prompt you are prompting. So it is doing a very good job of doing it. So before even double clicking on the chat GPT, how it is working underneath, uh, few key parts from the title itself. When someone says chat GPT, what does GPT means? So GPT basically is a category of models, large language models, basically, where the research started early on in 2018, 17 actually, when the transformer architecture was released. But GPT models were released around that time, so 18 or 19. And the whole idea of GPT is, if you expand, it's generative pre-trained transformer. So understanding this is very, very important. You'll keep on hearing different terminologies like generative AI and all. So what does generative means? Like, it basically means it's a language generation. So before we used to call generative AI, we used to call the category in the natural language understanding. Was there are two categories under natural language understanding. One is natural language processing, which is like understanding the text, classifying, extracting information. And there is a natural language generation. So NLP and NLG, you must have heard before. So NLG was the one where we were building models to generate text. And few years back, you must have seen on LinkedIn people posting Shakespeare novel getting generated using NLG deep learning models. They utilize RNNs, LSTMs, and all. So uh, what does GPT means? So GPT is like generative. It generates the content. It's pre-trained. Pre-trained means the model is pre-trained on Wikipedia, books, internet, content, documents. And the transformer means it follows the transformer architecture of the language model. And we'll go deeper into this shortly. So now we understand that GPT is a large language model. Why do we say large? Because it's trained on very large corpus. You can train a very simple small language model by taking one or two documents, train them, but their vocabulary will be limited to that, whatever is there in the document. But when you scan the whole internet, Wikipedia and everything, you are training on billions of records, billions of documents, your model. And model then can understand a lot of nuances, a lot of relationship details, domain-centric information and all. And that's why it's called large language model. And at a very, very high level, when we are building GPT-centric models like GPT, Llama, now Llama 3 is out yesterday. Um, there are like Gemini, all these different models, Anthropic's Claude is there. So all these language models are basically trained on large amount of data. So we'll talk about how do they train, and once they ingest all of this content, their model is basically, the transform models are running on GPUs, thousands of GPUs, training them, getting the right, if you understand the neural networks, the ultimate goal is to learn the weights. What are the right weights, so that model can learn from the content and finalize those weights so that it can predict, generate new content, and we can do the inference and all. So training with the large corpus, we build a base LLM, and then from that uh, base LLM now understands the language really, really, really well, right? It can correlate, it can generate the content, but still you need to while you are training this, let me step back. First of all, like when we are training the large corpus, let's say we put the election manifesto, and when the model is getting trained, uh, there are two type of modeling a model can get trained on. One is called masked language model, and other one is called causal language modeling. So in both cases, like you see a particular word, we take it out, and we try to predict, like when we are training the model. So model will try to predict in the mask language modeling. Let's say mask is hidden, and it'll try to predict which virtual word will come. So it'll be a word like which, sorry, masked word will come. So I'm a virtual assistant. So model will try to predict virtual. And if it's not predicting virtual, it'll go and just like any deep learning or any machine learning model, it'll try to predict some category. And if the predicted word is not matching, it'll find the error. It'll try to reduce the error by retraining to reach to a particular target label, virtual. And that's how, like in the masked language model, in between a word will be masked, and the model will try to predict and learn the overall language, how a word particularly is predicted when it's in a sequence of sentence, right? Same thing in the causal language modeling. The 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 model tries to predict the next word, and that's how it gets trained. So once the base LLM is trained on the language by either causal or masked language modeling, you do adaptation. So that's where the chat GPT, you see chat GPT, you can ask, create summaries. Sorry, I think is it someone there? Yeah. Mayur, can you want to say something?
I just had a question on that point. Two types of language modeling, right?
Mhm.
And in one of the model, like the first model, a word in between the sentences, kind of guessed by the model, and in the other one, the last word is right.
Correct.
So, what's the difference? Like, why there are two models? Why would do that?
See, again, this is a different strategies. We'll go deeper into the decoder model when we talk about the transformer. So let's keep your question aside, and you will learn
Okay,
that what is this auto-regressive learning process in the causal language modeling. ChatGPT is using causal language modeling, and we'll talk about
yeah,
the auto-regressive, the feature aspect. Okay.
okay,
All right. Cool. So, so what happens is, like, once your base LLM is trained, now you are doing the adaptation, and adaptation can be like a Q&A type of training, where let's say there is a large corpus of question and answers data sets available at Stanford, right? So you take that, you adapt the model to perform some of those actions. Same thing with the classification, summarization, modeling, translation testing. So translation training, all of these things, or chatbot centric. So you have a contact center, customer interaction data sets available. You can train your model, and you can fine tune to get a final ChatGPT style LLM ready. So, because our session is more about transformer, I will quickly rush through some of these slides. So, but I wanted to give a history so we all understand that it's not the Chat GPT which brought in the generative AI, but this whole paradigm about when the before even the transformer came in, um, we started with word2vec, FastTag, Glove, and some of you must have used some of these models to build word embeddings. So word2vec, Glove, all of these were like trained on large amount of Wikipedia or internet data sets to generate word embeddings to build the semantic layers more efficiently, so that models can perform really well. And slowly, if you see the hierarchy, like um, lot of companies, the BERT came in around 2019. We did use BERT at very large at one of the very large financial firm to build encoder centric models to for the entity extraction and classification for their corporate investment documents. So some of these BERT, Elmo, these models were used around 1819 timeframe. And encoder decoder architecture came in, where Google released T5 and Meta released BART. And some of these were initially used for transformer centric architecture. um, so encoder decoder architecture was released early, but uh, it started leveraging more attention centric mechanism, and we'll go deeper into that. But if you see the decoder only architecture, this is where the GPT and all those models came in. And right now we are using GPT-4, Llama 3 came out, Claude, Gemini is there instead of Bard. Um, so all these models, like how they evolved, it's very important to understand their pathways. And we will also understand what is the basic transformer architecture and how it spins into encoder only, encoder decoder, and decoder only type of different use cases. So it's very important to understand the use case and then incorporate some of those things in your modeling. So again, very brief history. Earlier, we were doing these language modelings. We were utilizing a lot of recurrent neural networks, and RN and LSTM. The main idea was basically you have set of hidden layers, and you are passing your sequences one by one. The problem with that was it was slow to train, and also it had a longer context problem, because as the context becomes longer, it can't hold the relevant information from the earlier text, and also it had like a big gradient decay problems. So sequence to sequence modeling came around 2018-19 time. There they built like encoder and decoder centric architecture, but again utilizing the similar sequential hidden processing layer. And then finally the new architecture transformer came along, which focused on only attention centric architecture, which solved the problem of the sequential processing of the words, and made it more parallel. So the biggest transformation happened. We call it transformer because it changed the way the data sentences were processed, by making it more parallel, by using attention, and attention will go deeper into attention aspect. What is attention? Uh, to generate more context. So the ultimate idea, if you see the language modeling, right, whether it's master or causal, whatever it is, our goal is to learn the language, its connections between words. At the end of the at the end, we want a representation of a sentence in the language, broader language spectrum, in a much more deeper manner, so that whatever machine learning vector we create, because ultimately machines only understand numeric numbers, right, numeric values. So we need to convert these sentences into numeric values, and numeric values needs to capture the wider context of a sentence. So if it's a very long document, if a sentence is talking about something and referring about a previous paragraph, uh, having the holistic context is always important. Then our model will be able to predict, classify, perform anything like summarization, creating new content, and question answering in a much more better way. So how can we capture context in a meaningful way in the vector is the main goal. That's where the transformer architecture came along. And if you see this architecture, you must have seen this diagram from the paper, which was released in 2017. So in this, there are two pieces. So in 2017, basically they released the paper primarily for a translation purpose. That can we improve our current encoder decoder architecture by just utilizing attention and making it more parallel to transform, let's say, English to French, right? And that transformation can use encoder and the decoder parts of this architecture, and we'll dig deeper into these things. So that paper was built for translation, but then eventually different companies utilized this, broke it down, and you used it for encoder only, decoder only type of different use cases. And ChatGPT is a decoder only architecture, and we'll talk about that. So you can cut off certain pieces and utilize this, and build use cases around it. So let's quickly go through that. We'll always refer back to this diagram and components so that we understand. But at a very, very high level, if you see what I mentioned, input sentences, if you are doing a translation, we'll cover the translation aspect. But ultimately, as a black box, input English language sentence need to flow through set of layers to get more and more context when it is converted from the beginning to a particular numerical vector represents only words. Slowly, we need to enrich these words with their positional meaning to attention, so that attention gives a contextual meaning. So final at the end, when we have the final vectors to perform any task, that vector contains all the information. That is the ultimate goal. So encoder only architecture is used for classification, sentiment analysis, entity extraction, and all those things. So we'll cover first that aspect, and we'll dig deeper into each and every layer so that you understand how this works, and we'll connect. So again, this is part of a sub part of the transformer architecture. Um, so if you see, how can we do a sentiment analysis, right? So before we treat this as a black box. So let's say we give a sentence to this uh, LLM to do the sentiment analysis. We'll say 2024 will be a great election, right? And what is the sentiment here? And at the end, like, the model will predict, okay, yes, it is positive. So let's quickly take a look at the code. So let's say if I have a code utilizing Hugging Face library, and you see here the code. Can you all see the code? Yeah, I think
Yeah, I can.
this should be visible enough. So if you see this code, like, we are using transformer libraries from Hugging Face, and it is utilizing a default model doing the sentiment analysis. A classifier is doing the sentiment analysis, and it's final resulting the label. And I always highly encourage everyone to basically go to the Hugging Face and utilize the transformers. Already on Hugging Face, there are a lot of models available, and you can see those models which are available here. They are all leveraging transformer architecture and providing support, like whether PyTorch, TensorFlow, what is supported, Plex, and there are lots of models available, and you can use these models. Like Llama 3 should be available shortly, but you can see all these models, you can leverage them to perform set of transformer-centric tasks, what we discussed earlier, like classification, translation, Q&A, and all those things. So simple example, if I go take this sentiment try to run this. So it is using the encoder only diagram, what I was explaining to you. 2024 election will be a great election. So it's running that, leveraging the transformer inference pipeline. So we are not doing the training here, but if you see, we are using a pre-trained model to do the inference. And I'll talk about both training and the inference aspect. And again, it's running on my Mac, so it's kind of slow. But if you see, it generated label positive. So if you go back to double click, like, what exactly this happening, like pipeline underneath the model, how it is classifying. So let's go back to our diagram. So if you see here, like, the first thing is we go through step-by-step processing. We take the sentence. Our goal is to convert that into the machine learning vector, which are numerical representation. So we go to the input embedding layer. I will go briefly on the basics of each and every part, and then we do the positional encoding, because position is also very important. Then we go through the attention layer, number 3. We'll discuss about the attention. And then we go to the final feed forward network, which is again a multi-layer perceptrons, which are fully connected layer to do the final classification. And if you see on the right side, I have put tables to show the vectors. But the most important part, when anyone is dealing with these natural language processing tasks, I always highly recommend that visualizing these in the vectors form, that where these words are lying in the vectors, the sentences and all those things. And what is our ultimate goal? Like, if you see the language in the multidimensional space, you should see words and their correlations in the vector space, and how they are correlated. If words are closer, they are more related. So the ultimate goal of all these machine learning models is basically to build a vector space where the representation of the words are um, properly laid out with their relationships and all grammatical relationships, tone, and everything. One second. So going back to the slideshow. So if you see, right, ultimately when we flow through these different layers, our final vector space when we are training this model. So let me talk about quickly, briefly about the training. So if you are taking this encoder only architecture, and we are putting a corpus where we have a labels already available for given sentences. We can train this model as like a neural simple deep learning or neural nets. You're trying to learn weights, so there are weights everywhere in the processing, and we'll explain how these weights, which are just like parameters which you are learning by looking at the outcome, doing the back propagation, reducing the errors, and adjusting the weight. So finally, when the model is fully trained, your weights are logged in, and then you do the inferences using those weights. So when you hear about like, okay, ChatGPT is trained on billion parameters like Llama 3, 8 billion parameter model, 80 billion parameter model. So there are multiple layers here where different weights get calculated, and we'll talk about those things, how these numbers can come from. So let's again go through step by step. Number one, the embedding aspect. So as I was explaining to you about the vector space, every uh, word we need to convert into numerical form, right? But just converting in the one hot encoding, like taking the vocabulary of, let's say, dog, puppy, cat in the whole spectrum. Let's say we have 50,000 words or subwords. Generally, a sentence get broken down into tokens, and tokens may not correlate exactly to the words, but could be a part of the word. So when we lay out our vocabulary, we can do a one hot encoding where each word is represented in one particular column. It could be a very long column, but it can be a very long row. And that word one can be part of one of the column, right? But that one hot encoding is not efficient. When we lay these out, we again build embedding models so that these word embeddings can be generated in a condensed vectors, and each word can be represented in a dimensional space at a particular location where the word is correlated with other words based on their semantic categories. So like for an example here, a dog and puppy are closely linked together, and when we say close, that means the cosine angle between these two words are smaller. So when you do the similarity and you multiply the matrix values, the vector values, you get the higher output. Because if you see, cos 0 is kind of 1, right? So cosine similarity, that's what we call it, cosine similarity. These words are closer compared to houses. Same thing, man and women are closer, king and queen are closer because of their relationship. So once we build these words into vectors using embeddings, we can lay out these words appropriately. So that is the first task, what we are doing here in the first box, input embedding. Once we have done the embedding and we got the vectors, but as I mentioned earlier, that the position of the word always matter. Uh, and if I say uh, Mary loves John versus John loves Mary, uh, even though the three words are same, but the meaning is totally different, right? So that's why the positional encoding is very, very important for model to understand where the word lies in a given sentence. And we do this positional encoding. And let me talk about positional encoding a little bit. So positional encoding, or like let's say sentence, I hit a ball with the bat, or I hit a bat with the ball. It's different actually, even though the words are same. If we feed the model with the plain vectors without positional encoding, it will not do a good job of um, uh, identifying the right context, right? So what we do, we leverage a kind of formula. We don't need to dig deeper into this. It's part of the transformer architecture formula, and there are a lot of experimentation has been done around it. But we can't simply feed like the numerical values like I is 0, hit is 1, A is 2, ball is 3, because then if we add those values to our original word vector, then uh, some of the values which are very far in the context can make the whole vector values very, very large. And that is not efficient, and that will not work. So what we do is we use a different pattern of sine and cosine values, alternate values, uh, and with the different frequency, so that we can still get the positional values in more floating point numbers way, in a unique manner. And we can skip this mathematics around it, but I'm just giving you a very high level part here, so that you can, if you are interested in knowing the whole history behind why the alternating different frequency centric patterns are used to identify the positioning. Ultimate goal is we need to know which word is positioned where, and if we can generate in a given sentence a right unique numbers, which are not far off, or very large, then we can easily communicate this position into our word vectors. So that's what we do here. We add it to positional encoding to our original word vectors, and it changes, like if you see the diagram on the right side I drew, it changes the positioning of the word, and moves the vector accordingly based on the positioning, so that we got nice vector representation of that. So once that is done, we got good understanding the word and its positioning, but we still lack the context, and the context is where the attention comes from. So I think you must have heard this term, like attention is all you need. It became a very famous phrase. uh, and so let's dig deeper into what is attention actually. And it's quite natural to us about attention, that when we look at a sentence, let's say 2024 will be a great election, our mind actually, our brain has neurons with, and again our brain has limited memory, so it can't capture everything and store it in memory. So it will try to attend to certain parts of the sentence and capture the highlights, and based on the correlations, our neurons will automatically see what are all more important and how different parts of the sentence are correlated to each other. And that is what all is about, attention is about actually, that what are you attending to in a given sentence. And once you get these key values, uh, you can easily answer questions, right? So the paragraph initially was, which we saw, if I paid pure attention to certain key salient features, I can answer any question around that paragraph, right? So if you see the attention, like this example, the animal didn't cross the street because it was too tired. So every word actually in this particular sentence is related to each other. Like, so when you see this example, it is correlated to animal, um, because it was too tired, and also why it did not do it, because it was tired. So there is relationship between each and every word with the other words, and those relationship is what we need to extract and put it in our vectors to enhance our word vectors with the enough contextual information. So that is what is attention all about. And how do we do it mathematically? um, Again, as I mentioned earlier, the word vectors are lying in the vector space. And when we do the cosine similarities, we can get bigger values by doing the similarity calculations. But there is also one more part, because it's not just the words when we are doing the similarity calculation. Also, we need to multiply these things with some learnable weights, which can be trained by the model. When you're training the model, based on it, it can be used. It is a very common thing, right? But when model is trained, it can easily correlate to the given subject, like animal or some person or someone. So these weights are also very important. So there is a concept which is like very confusing to people when we do the mathematical calculation of these attention in our transformer model. The concept is query, key, and values. And I would like to explain that in a much more simpler manner. The correlation is to simplify things. So let's think about a very simple way. Let's probably open the paper or something, Jamboard. So let's say, um, or I think that we can open this Canva. So let's say we we have a database, You can think of this as a key value pair database. Key value. And we can have different categories. Let's say there is a romantic category with movie Titanic. Sorry, it's really bad, but we can understand. And then we can have a query. We can query the database that, okay, give me movies about love. So when we query it, it gives us, we query the different keys. Let's say there is a horror there. So when we query different keys, we can see, okay, this matches closer to the romantic, and we can get this values Titanic, right? So this is kind of a modeling in which our transform models are also uh, utilizing the mathematical modeling to get the attention. So if you just go back to the diagram, what we are doing here, we are taking the query Q, which let's say it, right? So the query is how it is related to the animal. So when we say animal, so it is saying, let's say, how I'm related to all of the words. So it is a part of the query. It is a part of query Q, and all the keys are rest of the words in our, one second, in our sentence, the animal. So all of these are keys. So it then goes and does the similarity multiplication with these vectors. Again, this is a matrix multiplication, and it gets some values like multiplication values. And so if you see here, Q and keys, all these keys are multiplied together, uh, and we get the attention, these different values, how they are correlated in the vector space, these words, right? And then finally, what we do the ignore the softmax and all. You probably understand softmax is basically to standardize all the values into a particular probability spectrum of 0 to 1. So we will do this, we'll get the probability weights out at the end when we do the multiplication. So once we get that, okay, just like our example of romantic to Titanic, right? So we'll get a higher weights for Titanic. And when we multiply this with our final value, which is again the sentence, we'll get a weight distributed value, which is attention, uh, which is the information of the attention, which we are capturing in the word vectors. And that these word vectors are our final value. So we got the initial word vector, which is the value. We multiply this with our information for every word with the query and keys, get the attention metrics, and we multiply the values of each words, value of the each word vector with that probability distribution of attention of that word in the vector, right, space. And then we get the every word gets the value, and we finally have an attention encoded for each and every word respective to the others. So this is a very complex part, but one second. I think this probably give a much more better visual. So if we have all these keys are, again, the words 2024 will be a great election. Query, again, we'll pick one word at a time. 2024, let's say we pick, and we go and multiply with each and every key, uh, and we get the similarity scores. We apply the softmax and we get the weights, and then we can multiply this with our original values, like 2024 will get multiplied, and 2024 vector, initially it had only the word semantic meaning. Now it has the attention also encoded in its vector space. So ultimately, once we do that, we get our final attention encoded vector. So original word embedding vector at the end gets the attention encoded vector. That is our ultimate goal. Once we have that information, because now this vector is super rich vector at the end, and we can do the classification. So here we are doing the classification, right? So we can do the classification in feed forward layer. But understand one very important part, that simply multiplying these things, getting the weights, that is only one thing, but there is a part called trainable parameters. So if you see each and every layer, when we are multiplying query with the keys, we are also multiplying queries with a weight matrix, key with the key weight matrix, and value with value weight matrix. So why those weight metrics are important? Because those are all learnable parameters. So they will, during the training time, they will get adjusted to reduce the errors. And finally, we will, just like our neural networks, where weights are there in each and every hidden layer, here also we have weights in query, key, and value um, steps. And during the training, those weights get adjusted. And finally, once the model is trained and when we are doing the inferring, those weights then try to predict or try to encode the attention in a much more better manner. So that's how the single head attention works. And we'll talk about why it's called single head and multi-head. So in our diagram, it was mentioned that we are using multi-head attention. But let's jump through that part. So head is nothing but like this query, key, and value, these three things, same vector. Everything is similar, it's just how the operation is happening. They are now spread across in multiple layers. Uh, so just like you saw the sentence, right? English language, like, or any language, uh, the relationship between words is not just one dimensional. Like we can build, there could be a grammatical relationship, there could be tonal relationship, there could be domain-centric relationship. So there are different relationships within a sentence between words. So we did a good job of capturing the attention in a single manner of a sentence, but can we capture all of the different form of attentions, right? So what we do mathematically, we again have a different heads, and heads are nothing but the layers where we are doing these calculations to capture the attention and then encode into the word vector. So what we do in multi-head attention, we have these different heads or layers running in parallel, pass getting, and the important part is each layer has different weight matrices. So we talked about query weights, key weights, and value weights, right? So each and every layer has different weight matrices initialized during the training time randomly. And then uh, during the training time, all of these different layers will learn their weights to capture the different form of attention within the sentence and the relationships. So once all of these attentions are calculated by these individual layers, uh, they get we do the softmax and we finally concat all of them, because ultimately we need to get, we input a word vector, we need attention, all of these attentions also encoded in our final word vector. So we have a very rich vector available to us. So that is where at the end of the day we got a rich vector available to us to perform any type of final calculations, content generation, classifications, and all those things. So this is what like multi-head attention is all about. It's just the set of layers. So if you see Chat GPT and all, they're using like many heads in parallel. One of the example which I will show, like we are using 8, but in some cases 64 is commonly used. And all of these weight metrics, why the billion parameters? Because if you do the calculation, all of these weight matrices, uh, different weights with different heads, different layers, and the word vectors, generally when we embed, like each word can be 512 long vector, and all these weights are accordingly laid out for those vectors, so that when we multiply, all of these weights combined together are becoming more and more parameters, right? So each and every weight in this metric cell is one parameter. And when you see ChatGPT trained on, let's say, 100 billion parameters, so there are so many heads, so many weight matrices in attention layers, feed forward layers, all are getting trained. And even when we do the final projection, so here in this diagram, if you see, once we concat and we do the final projection, we have another weight layer. So these are all different neural net layers with their weights. They need to be trained and projected. So that's why, like, more parameters capture more and more values and let the model learn in a much more better way. So once we have done let's go back to the diagram because this is the part that's very important. So step 1, 2 is done, attention is done. You see here, we got the attention done. Now, after every box in the diagram, we are doing this normalization process, like whether it's a feed forward or attention mechanism. And the whole idea of this normalization is to stabilize the outputs. And the stabilization part is basically there is a residual component, like we take the inputs and then we add it to whatever is coming out from the multi-height part. So we add it and we normalize. Um, I'll keep it at a very, very high level. We don't need to go deeper into normalization part, but there are different normalization techniques available. Batch normalization is there, layer normalization. We are using layer normalization, which is much more faster, which is feature-centric normalization. But again, think about this. Normalization layer is, if you know the deep neural nets, there are a lot of problems with how these numerical values, they go out of hands. And every single time, like, you need to normalize them, stabilize the network so that training can become faster and move forward. So that's what this normalization layer is. I'll not spend too much time on that, but give you a visual around it. So we have a layer normalization, which is feature centric. So you see here, like, if there is a batch of values, uh, instead of going across, we are just going down in the same feature set, and we get the mean and standard values, and we apply this calculation to stabilize the values so that it can go to the feed-forward network. And feed-forward network is a very typical multi-layer perceptron layers, like fully connected layers, just like you do train any simple model with TensorFlow, Keras, or PyTorch. You build these hidden layers, drop out some, apply the activation function. So all of this it's doing is it got the input from the attention layers with the rich information, and then it is trying to project uh, based on the whatever label we need to generate, like positive, negative, and all. So that's like pretty straightforward. We don't need to get into details about this. I would like to capture the other things very fast because will be late in this session. So just like we did the classification with the encoder only architecture, we can also do entity extraction. We can train the model, we can train it and give the targets as a determined entities like person, location, company, and all those things. And model is trained, then it has all the weights available to model in the encoder only architecture. Again, the same thing. If we pass the text, Biden and Trump will be in Washington, D.C. It'll flow through the similar input embedding, positional encoding. We got the context, attention added to the vector, and in the fully connected layer, it'll try to detect each and every component of the text. Now comes the decoder-only architecture. This is what ChatGPT uses. This is what does the generation part, and it's called generative models. So how do we do that actually? So ChatGPT, if you see, right, the first example, what we showed, create a 50 word summary for the US election, and it generated a text. So how do we do that in under the hood in transformer architecture? So just like encoder architecture, it's similar to encoder architecture where we are taking the sentence, we go through the embedding, and we add the positional encoding. We already covered that. Then we do the mask multi-head attention, and I'll go deeper into this quickly. And then we follow through the feed-forward network and try to predict the next word. So as I was talking about the causal modeling earlier, right? So the model, when it is training on the large language set, the decoder-only architecture model, what it does is it will take the sentence, let's say, when is election? Already the sentence is known. It will hide the election and will pass in when is the election to the model. And at the end, it will expect that election is predicted. And the error calculation, back propagation will fix all those parts, and then we'll train the weights and all in the model. And the model will be able to generate this. So it'll generate election, then election will be fed back. The whole sentence will be fed back. When is the election? And it'll try to predict um, basically the next word. So if you see, right, in this example, let's say if I'm giving a prompt, when is the election? After going through I've trained the model in election documents and all. And if I ask, when is the election? And there are certain key parts in a sentence which we always pass it to these models. One is the start of the sentence, SOS, and other one is the EOS, which is the end of the sentence. So let's say we pass the marker prompt, when is this election, and with the EOS marker. So the model takes this sentence, applies all the encodings, attention, and then basically like it'll try to predict the next sentence, which is 2024. And let's say if he needs to 2024, it is auto-regressive because it'll take 2024, it'll feed it back to the embedding layer, and it'll generate the next word, let's say 2024 November, right? So it'll try to predict the next word November, and then it'll try to predict, let's say, EOS, end of the sentence. So it will generate answer 2024 November. So this is the decoder only architecture, which is auto-regressive, which will keep feeding whatever sentence is generated. So in ChatGPT, whenever you type something, you have seen, right? It is typing constantly the answer. Because it's getting those values out from the decoder, and it's feeding the remaining pieces constantly to generate next word, next word, next word, next word, and that's why we call it auto-regressive. And while training, so I'll talk about some of these layers. We already talked about embeddings, positional encoding. Let's talk about the mask multi-head attention. So attention is, when we talk about attention in transformer architecture, there are three types of attentions. Self-attention, which we discussed earlier, where every word will go through and scan the other words for the key and query multiplication. There is a mask attention where in the case of decoder, uh, let's say we are passing a sentence, when is the election? And we will just want model while training that it needs to predict election. So we mask election from the input embedding. So we pass it, but we mask values which we need to predict in a given trainable data. So we will put minus infinity in place of election, and it'll be zeroed out. So when we create a final vector in feed forward network, it'll be only till when is the, okay? And that's why it's called masked, because we are masking certain pieces so that we can predict that word. And then, so our errors then can be calculated based on whatever the prediction word we are looking for election versus whatever model is predicting. And that's how like the whole training of the decoder based architecture works. So let's quickly look at this. So in case of self-attention, I already told you, like we go through each and every word. In case of mask, we are removing what we need to predict, because when is the, we don't want a model to know predict something based on the future value, because that is what it needs to generate. So none of the future values should be fed into the model for the prediction part. So that's why like in decoder, when we are doing the content generation, we have to mask these out. And there are functions available to mask out in the vector matrix. So let's say life is short, eat dessert first, right? So we need to, when we are predicting step by step life, we pass it to decoder, it needs to predict is. So in that case, we mask out all the rest of the words, like is short, eat dessert first. Same thing when we are passing life is to decoder for next word short, we keep on doing that, and we are predicting next word and finally training the model so that it can generate this kind of data, and it can learn the weights to do the right content generation. So this is mask attention, you will see. And same thing with the multi-head, because it's running in parallel, it's doing all those learnings of different correlations of a given data. Then it can do the content generation aspect. Then finally part is like, how can we combine these encoder and decoder? So encoder only architecture has certain use cases, decoder has certain use cases. But in case of language translation, we have to combine these two things together. So let's say if I pass a language sentence, I love you, and I want the answer in French, je t'aime. So this is a very basic example where I love you will flow through the encoder, and we already went through the inner workings, input embedding. We will add the attention values to our vectors. We'll get the final vectors done in feed forward network. It'll learn it'll collate everything together, and it'll basically pass this I love you vector to the decoder side. And we'll talk about the cross multi-head attention in this case. But let's go through the decoder side. So when I love you is passed to the encoder side, decoder side always we pass in the beginning a start or SOS, because we don't know what next word it should be, right? So we pass SOS, and it knows that it needs to translate, because while it's training, let's say we are building a model to translate English to French. So while it's training, it knows that it needs to train on je t'aime. So but Because it's a mask modeling, it'll always start with SOS, start of the sentence. It'll pass it up. It'll do the mask multi-head attention. So that means your them is totally masked out. And it'll get the context from keys and values you see here coming from I love you English, whole vector sentence with the attention in the cross multi-head attention. So there, once it captures the SOS, because as SO has no context right now, so mass multi-head attention will not capture much. It'll pass it down as a query that, okay, this is my start sentence. I will multiply with each and everything in the context of I love you with the vector values and encode that, and finally pass the encoded vector from the original language vector and whatever my beginning part, and I'll try to predict first word. So it'll predict J, right? Je. So it'll pass it down again, auto-regressive. It'll pass it down both SOS or start or je, and then it'll go through the same thing. Now you have these je available in the attention, and then it will use the same full context I love you, because the encoder is done. The sentence is already passed, vector is created. We are always going to use the same I love you vector while doing this auto-regressive decoder flow. And then it will basically do the same normalization and try to predict them. And it'll complete, and at the end it'll say EOS. So it converted all the sentence. So it follows the same thing. Let's just dig deeper into the cross multi-head attention. The process is exactly similar. It's just we added this cross multi-head attention, because if you see, for translation we need a full context of the original language also. While we are training, because we trained all of these things, the model weights already knows like how these different words, their sentences, they are correlated in language translations. So when we are passing for inference a sentence, uh, the word vector where we are searching, like query je query is trying to correlate with the I love you keys, and then it'll find the right probability weights to multiply, to basically add it to the values for French. So, and these value weights will then be able to predict in the feed-forward network them for the next word. So it follows the similar pattern, but if you see the cross attention, the value and key vectors are right now coming from the encoder side, and query is coming from the decoder side in translation space. And basically query, we get the attention energy, we multiply with the key of the whole sentence, and we finally merge these probability weights to our value to generate and predict the right language, the next word. We have only a few minutes left, so I will skip this part, which we will cover in next set of sessions. So multimodal is basically like we are just talking about the language right now, but now with a lot of LLMs, we can generate image to text, text to image, videos to text, audios to text. We can do all of these things. That's why it's called multi-model. That means it's not just one type of input. The model can take multiple types of inputs, and we will go through how models are trained by chunking either the audio waveforms into the smaller pieces, or we can generate small patches of um, text or images. Videos can get into frames, and frames can have further images. All of these things are fed and trained to the similar kind of transformer architecture, but there are certain pieces, and we'll cover some of those things. And also there is a new attention mechanism, or enhancements to the attention mechanism has been proposed and used by Gemini. We'll cover that infinite attention, where uh, we were going through the query keys on the right side of the modeling, but we added a compressive memory so that we can capture even longer context, like billions of uh, text elements we can capture, and then we'll be able to apply the same model on a very large document. So right now what happens is, like, we have to chunk and align with the token limitations of ChatGPT or certain models. Once models implement the compressive memory or infinite attention, we'll be able to perform this on a very long set of tokens. Then it can parse very large documents, complete source code of a project. So I was attending Google Next last week, and there they showcased the Gemini, where it can basically parse the whole thousands of lines of codes, or like thousands files basically in a code base, and it can generate new code. It can parse large amount of documents in one shot and get the answers. So exciting times ahead of the on the transformer architecture, and new models will be coming soon utilizing this. But we'll capture more in detail how compressive memory utilizes this, and then we'll talk about the adaptation of LLMs, fine tuning those using LoRa, QLoRa, how companies are using these LLMs, and modifying those things. So we'll cover certain use cases in the later sections. I'll just conclude this here with like these are some of the clients we have worked with, and we have teams spread across. We are a consulting company also, and a product company. So happy to be here and passing some of this knowledge. Quick set of questions and answers. We can go through that. I'll pause it here. But I wanted to quickly show also one more tiny transformer. We'll open it up on our GitHub location. So we have a Insight Lake GitHub location where we release a lot of products or code base, what we generate for wider community. There are 70 repositories. We'll be releasing LLM tiny transformer example, but let me quickly show you that transformer example. So if you need to build it yourself and go and look at the inner workings, we looked at a theoretical perspective through the architecture, encoder only, decoder only, encoder and decoder centric. But this is like a simple tiny decoder only transformer mimicking ChatGPT. So if you look at this model.py, let me just increase the. Okay. So this is a model.py where it is doing the same causal self-attention. And if you see here, the layers are laid out. So let's say this is the GPT layer, and the model is basically, it's built on PyTorch. And if you see the forward layer, what it is doing, I'll explain you quickly. 1 second. Layer norm, forward. So let's talk about this forward part. So if you see here, what exactly we are doing, we are taking the model, we are, I think where is this here, attention. We are embedding those things, we are adding the positional embeddings, and then finally we are generating query keys and values and adding those things together, and then doing the forward prediction and all. But this block is what you can think of. So we create a block, train the model, and we generate the content. So if I quickly run this and I'll show you what it is doing. So if you see the block, it is doing the layer norm, and then it's generating the attention, then it's doing the layer norm, it's doing the feed forward. MLP is nothing but the multi-layer perceptrons layers. And then it is at each and every forward layer, if you see the block, it is appending the attention. This is the residual layer. Once we calculate the attention, we add it to itself, and then we go to the feed forward layer. So the code you'll be able to run, it's a very tiny transformer where instead of words, it's training on characters, and it predicts next character. So if you see here, I just ran it, but you can run it again. So it will try to generate set of sentences. They'll be random because I'm running on Mac with like few CPUs only, CPU cores, and it's not trained because the number of epochs or layers are less compared to a regular model. But if you increase those, you will see the errors come, the error values, those things come down, and precision improves, and it will be able to generate a good word. But I ran multiple times, so you can see it's generating still good words, that we pray, mean. So it's generating good English sentences because it learned the character sequences, how they come across, and it is building the attention mechanism on a given sentence with those characters. So it's a very simple tiny transformer implementation. I will publish this to our GitHub page, and you guys can play around. But this will give you wider insight into what exactly we are doing, like how we are generating the keys, how we are doing the masking, and how we are doing. You see here, we are doing the scale dot product for getting the attentions, for getting similarities, and finally we get these values. Attentions are calculated, and then add it back, and then we do the softmax and do the typical machine learning modeling aspect. But and also one more important thing is, if you want to visualize, there is a Python notebook available where you can visualize the attention. So and you can use those Hugging Face auto model and auto tokenizer, play around with this, and you can see each and every word in a given sentence, how they are related to other words and what kind of attentions is there. And if there are multiple layers, you can go to a particular layer and see the attention metrics. And so this visualization also gives you highlight like what model is exactly doing and what it is trying to capture as an information at the end. But attention is nothing but context. We are getting the information out of the context on the sentence, capturing that into the word embedding so that it's a nice vector with all the words information, their relationship, context, details around multiple dimensions. And that vector, now you can use it for a variety of tasks. That is the ultimate goal of this whole architecture. I'll pause it here. Any questions? Well, if not, then thanks a lot for coming. And if you're interested, I'll do next set of sessions, and we will continue learning series.
Yeah, thanks, Vijay. This was very informative. I was struggling to get right set of information on internet. This session was wonderful. I'm definitely looking forward to the next session.
Awesome. Thanks a lot, Mary. All right.
Thank you.
Thank you, guys.